I mentioned that knowing the population standard deviation allows us to better understand the sample distributions. So, one of the assumptions that I made in order to use this formula, calculate the standard error, was that I had to know the population standard deviation. Okay, and it was like my standard error was affected by my sample size, because bigger sample sizes, the smaller the standard error is, the more squished together the distribution of the sample means is. But I started out needing to know that in order to set up this rule and work with my distribution. We don't always know the population standard deviation. Sometimes we only know the standard deviation for the sample. Okay, so let's say I sampled 25 people, right? I don't know the population standard deviation. That's unknown to, well, I do know that the mean for those 25 people came out to be, I'm going to call it 60. And I do know that the standard deviation for those 25 people came out to be, I'm going to call it S, small s. Okay, came out to be, let's call it 10. Okay, so now that's for that sample. That's for all the people in that sample. And I know that this mean approximates what mu should be. And since it's a random sample of 25 people, I'd expect the same amount of variability in my sample as in the general population. Get some, the same spread in my sample as the general. So this approximates the standard deviation. Well, when we did our confidence interval, we had to live with the fact that we didn't know this, that was never going to be known to us, right? But we wanted to make sure we knew the standard deviation because we didn't want to introduce more uncertainty. Now, if we don't know the standard deviation of the population either, and we use the sample means standard deviation to approximate it, to substitute for it, so that our standard error is going to be equal to S instead of sigma over the square root of n, right? Well, that extra layer of uncertainty has to be adjusted for. And the way that we adjust for it is that we have, in calculating that, instead of using the z-scores to calculate the spread of these samples, we're going to use something, instead of using a z-table, we're going to use a t-table. And that t-table, now if you can imagine, the bigger the sample size is, the more confidence that we have in the sample standard deviation, just as with the mean, being close to sigma. Get a really, really super big sample, we get pretty confident that we have a pretty good handle on what the population standard deviation is. But as we get a smaller sample, we have less and less confidence. So we have to, when we say calculate a confidence interval, we have to make our interval wider to account for that that difference in the level of certainty that we have. So I'm going to pull up the t-table. Okay, I think I have one open down here. Here is the t-tables, I think. Here are the t-tables. Well, in reality, for every sample size, there's a different t-distribution. So I'm going to start out with, that if I wanted to find a 95% confidence interval and I knew sigma, I would say that I'd start with the mean of the sample, which was in this case 60, right? And I would go 1.96 standard deviations in that direction, 1.96 standard deviations in that direction, calculate my standard error, and multiply 1.96, and find out what my range is going to be. In other words, my margin of error, the amount that I'm adding to 60 on either end, is going to be, well, let's see. Let's calculate it right now. S is, if I don't know my population standard deviation, I'm going to have to use S, which is 10 over the square root of my sample size, which is 25, which is 5, and that's equal to 2. So my standard error is equal to 2. So I would use 1.96, right, plus or minus 1.96 times my standard error, which is 2. Okay, that's what I would be adding. That's my margin error. That's what I would be adding to 60. About 4 below and 4 above. Well, now, I said that, I can't have that much confidence. I need to spread this out a little bit. And the sample size is what gives me a higher or a lower level of confidence in the spread of this sample distribution. Okay, so now, if I have a very large sample distribution, if I have an infinite number of samples that I took, see if I can get this to scroll up. If you look way down here at the bottom, I'm gonna narrow this a little bit so we can, let me see if I can't get the bottom here and get it to crank up a little bit there. There we go. I'm going to scroll up here, and we're looking at 95% confidence interval. Notice it also gives you what you need for a 90% confidence interval and a 99% confidence interval. If I scroll all the way up to the bottom here, I'm looking over here and I see, let's see, 1.96, right? Well, that is a very large sample, means that I have so much confidence in the sample size that I took that I'm going to use that. I'm going to just make believe I know the population standard deviation. But as the sample size gets smaller, I have to be a little bit more cautious about this. So if the sample size is 100, whoops, oh no, what did I do there? Is it back here? There it is. If I get a sample size of 100, I'm going to use, well, here's 100 right here. Actually, tell you the truth, this is not strictly sample size. It's actually the sample size minus 1. It's called the degrees of freedom. Now, they could have put sample size here and just adjusted all these numbers, but you chose to use degrees of freedom. So really, when I want a sample size of 100, I'm really going to look up 99, but 100s, they don't have 99 on here. We're going to be stuck with this. So instead of using 1.96, because that sample size of 100 is not, no, I still have pretty good idea what the population standard deviation is based on that sample, but I don't know it as well as knowing S is the standard deviation of the population of the sample, the 20 numbers or the 25 numbers. Standard error is the standard deviation divided by the square root of n, the spread of the sample. I'm just answering a question that was asked. Okay, so for 100, I would use 1.98 instead of 1.96. For a sample size of 50, right, I would use, let's see, 2.09. See, that number's getting bigger. As that number gets bigger, then you multiply it by the same standard error that you calculated before. It's going to give you a wider interval, a wider margin of error that you add and subtract. So your confidence interval gets wider. Okay, if I have a sample size of 25, well, gee, it's 2.06 I use instead of 1.96. If I got a really small sample size like 4, well, that would be 3 degrees of freedom. And I would use for t, I would use 3.18, a number much larger than the 1.96. That makes my confidence interval wider, and it makes up for the lack of certainty that I have by only using the standard deviation of a sample of 4 numbers to estimate my population standard deviation. So what does this mean for us in real life? What this means for us is, in this particular example, since my sample size is small, it's only 25, right? I calculate my standard error based on my standard deviation of my sample, which was 10, divided by the square root of 25, which is 5. 5 into 10 gives you 2. So my standard error is 2. So my confidence interval is 60 plus or minus not 1.96 now, since it's 25, which means 24 degrees of freedom. 24 degrees of freedom, I would use 2.064 for my, I wouldn't call it a z-score anymore. I would call this now a t-score, right? Plus or minus t for alpha is 0.05 for 95% confidence interval. T times the standard error, okay? Or in other words, 60 plus or minus 2 point, what was it again? 2.06? 24, 2.064, 2.064 times my standard error, which was 2. So that's 60 plus or minus 2.064 is 4.128. Okay, so that's going to be on one end, it's going to be on the high end, it's going to be 64.128. And on the low end, it's going to be, let's see, 55. I'll do it with a calculator so I don't strain myself. 55, let's see, 60 minus that margin of error of 4.128 or 55.872. Okay, that's my 95% confidence interval between 55.872 and 64.128. I'm 95% confident that the true mean for this population is between these two numbers. Had I known this population standard deviation, even though it's a small sample, I could have used 1.96 and I would have got a narrower range, which would have been very nice for me. But since I didn't, I had to use the t-score instead. Well, what do I do for a 90% confidence interval or a 99% confidence interval? Well, the only difference there is instead of using the 2 point for the sample size of 24 degrees of freedom, instead of using 2.064, well, let's see what I would use instead. 90% confidence interval, in other words, T means 5% on either side in the right tail and the left tail, right? They're always symmetrical, so they just mention right tail here, but we know that really means both sides. So 90% confidence interval means 5% in the upper tail, lower tail, so it's going to be narrower than a 95% confidence interval, which is 2.5% on the bottom, 2.5% on top. What would we use for a sample size of 24 degrees of freedom? We would use 1.711. What would we have used if we knew the population standard? We would have used 1.64, right? So this gives us a wider interval for the 90% than we would have had if we knew the population standard deviation. But we want that. We want to make sure that we account for that extra level of uncertainty. And how about 99% confidence interval? Well, this is 99% confidence interval. Instead of 2.58, we're obviously going to use a bigger number. We're going to use 2.797, okay, to calculate our 99% confidence interval. Okay, so that's how we would do this and use our t-distribution and table to calculate a confidence interval. Where do we use the t-distribution? We use the t-distribution instead of the z-distribution. We use it when we don't know the population standard deviation. Really, that's where we would use it all the time. That would be swell if we used it that way all the time. However, as statisticians, we allow ourselves to take, a little bit of latitude with this. Okay, in that, if we have a very large sample, right, then I would say, as these numbers get bigger and bigger, if you look at the table, as the sample size gets bigger, the t-score, the t-value, becomes closer and closer to the 1.96 anyway. So if you have a sample size of 100, you may say to yourself, well, to save time in my initial calculations, I'm not going to bother to go to the t-table. I'll just use 1.96. So the two places where we would use a z-score, or three places where we would use a z-score is, number one, and most often, is if we knew the population standard deviation, or we were told that we knew it or had a very good estimate of it. If we have a very large sample size, and a very large sample size can mean a lot. You might say, I think a large sample is 100, or I think a large sample is 50, right? In many applications, anything over 30 is considered a large sample. So if you get a sample size over 30, you might be able to take the latitude of saying, I'm not going to bother to go, spending time looking up for the table. I'm going to use my 1.96 and my 1.64 and my 2.58 for my confidence intervals. Okay, so I might stick with those instead of actually sitting down and calculating looking up at the table and using that to calculate my confidence intervals. Okay, so for the time being, it's best if you use the t-score if you don't know the standard deviation. But in a lot of cases, once we get a sample size over 30, you'll be able to ignore that and just use the z-score instead. Anybody remember what I said the minimum sample size has to be for calculating the confidence interval of a proportion? What was that sample size I said you had to have? Anybody remember it? Remember I said each group had to be at least 15. So overall, we had to have a sample size of, right, it's binomial, so there's two groups, 30. Isn't that the number I just mentioned that said we could take latitudes with this? When you do the proportions, when you do confidence interval for proportion, right, you always work with a sample size greater than 30, and each group is greater than 15, is at least 15. And that gives you the latitude to use 1.96, 1.64, and 2.58 all of the time and not bother with the t-table when you're using proportions, provided you stick to that sample size rule. Okay, so that's the only twist on that for proportions. So now I'm girding my loins now when I ask this time. 0 to 10, how well do we think we know what we just went over? Let me look at these comments also. Give me some feedback. As I'm going back and reading the comments, give me some feedback on 0 to 10 on this portion. Okay. By group, you mean each side. You get dichotomy, or by dichotomy means di means 2, bi means 2. Same thing. Yeah, so anytime you have a choice of 2, that's how you get a proportion, right? Proportion is always, it's either this or that. What proportion of the people in this society have green hair, right? They either have green hair or they don't have green hair. So it's 3% have green hair, right? Or what proportion are HIV positive? Well, in this population, the proportion is 3%. It happens that we call that a special kind of proportion. We call that a prevalence, but it really is a proportion. It's just a percentage. Okay, 6.5, 7s. Okay, not as good as we were on the other, but this is the most challenging part of this, is implementing that t-table. Okay, so for the t-table, you use the t-table anytime you don't know the population standard deviation. However, you don't need the t-table if you're willing to roll the dice and say that if my sample size is greater than 30, I'm just going to stick with the z-score. If that's not acceptable, like on an exam question, if the sample size is greater than is like 35 or something like that, or 36, if I don't want you to use 1.96, use the z-scores, and I want you to go to the t-table, even though it's a sample size greater than 30, I'll warn you. I'll tell you that. Okay, so you really want to know standard deviation in all cases if you can, because that's a more accurate measure for us. What is the appropriate end? I think that answers that question, right, Jenna? Right? So anytime you don't know the population standard deviation, you can go to the t-table. In fact, if you look at the t-table, it goes all the way up to a sample size of infinity, right? But for our purposes, if you get over 30, you can stick with the z-score, unless I tell you differently, unless I tell you I want you to use the t-table. Anybody want to hazard a guess at what sample size that SPSS crosses over from using the z-score to using the t-score when it calculates the confidence interval? What sample size do you think it uses when you use a program like SPSS? I got a 30. Sounds like a decent, like a good idea, right? Because that's the rule I just gave you. 15 for each group, maybe. I don't know about 15 individually. Remember, because we want that sample size to be decent. The fact is, the SPSS is a computer. It doesn't need to save any time or energy calculating stuff. Okay, we are exactly for each group. It doesn't need it. SPSS uses the t-table for everything. It doesn't care if the sample size is 2,000, and instead of using 1.96, you should be using 1.9605, right? It's going to do that extra precise measurement. it always uses the t-score, never uses the z-score when you're working with a sample, right? Because it has, it doesn't have our constraints of time and energy and decimal places. So, but that's how SPSS would resolve that. We're eventually gonna move on to